Okay, hi everyone. So I'm Stefania, and during my PhD work, I study on the stellar population properties of bulging disks in the semi-cluster galaxies. My advisor was Matt Owers. I was at Macquarie University. And this is a picture of me the day I submit, and I think I drink like this of wine, and then I slept for like 16 hours. And so there's two questions that we wanted to address. One was why are bulges rather than disks, and we found that it's due to their enhanced metallicity compared to difference in age. And the other question was related to the formation of S0 galaxies in the clusters. And we found that it's the processes that act within the central region of the clusters and that act on the disks that mainly are responsible for the formation of these galaxies. So this is all my PhD work in one slide. And now what I actually want to talk about is how the bulge formation correlates with spin filament alignments. So this is, I'm now a postdoc at ANU, and this is a work in collaboration with Matthew Colles and the SAMI team. So the motivation of this work is how do galaxies build up their angular momentum within the cosmic web? And the two questions that we want to answer here is what is the primary galaxy parameter that mainly correlates with spin filament alignments? And by these last three words, I mean the alignment of the galaxy spin axis with respect to the closest cosmic filament. And then if we go more into detail, what can we tell about the spin filament alignments of the galaxy components, such as the bulge and the disks? Now, first of all, we need to reconstruct the cosmic web. And to do this, we use the redshift spectroscopic gamma survey. And we are interested in the local universe. So we just use galaxies up to redshift 0.1. And okay, let's see if I can have this one running. Okay, so we exploit their 3D coordinates, such as right ascension, declination, and redshift. Okay. And so what we did was we reconstruct the density field by the Leonid oscillation, and this is the three equatorial regions, and then we use disperse as a structure to reconstruct actually the cosmic filaments of the universe within the gamma regions. And these are the 3D models of the density field and the cosmic filaments. So just quickly on disperse. So it has been used a lot now, more than 10 years. And astronomy loves to use disperse because it doesn't make any assumption about the distribution of galaxies. And this is something we usually like. And then we also allows us to put cuts on signal to noise so that we can extract the most robust features. And that's something we also liked. But so it's on GitHub, and it also has its own website. Now, then, to identify the galaxy spin, we exploit the SAMI survey, in particular, the specially resolved stellar kinematics. So here is an example of a velocity map for a galaxy where the black line represents the projected spin axis and the green line represents the kinematic position angle. And we can measure kinematic position angles for around 1,000 galaxies, so we can study the alignments for around 1,000 galaxies. And to go into more details, so to look at the separate bulge and disk spin filament alignments, we took advantage of 2D decompositions, and we have both photometric and kinematic decomposition. So with the photometric decomposition, we can measure the photometric properties of bulge and disks, such as the fluxes. Instead, for the kinematic bulge disk decomposition, which has been done by Shri Ho for the SAMI survey, we can actually separate the kinematic maps for the bulge and the disks. So we can measure the separate spins of the galaxy components and the separate alignments. So this is a projected representation of what's going on. So these are the free gamma regions. In blue are the cosmic filaments that I have reconstructed. And in gray, the gamma galaxies that I used to map the cosmic web. And in red, the semi-galaxies for which I want to study the spin filament alignments. So then we need to assign each semi-galaxy to the closest cosmic filament. And we did this in 3D Euclidean space. And then we measured the angle between the angular momentum of the galaxy, so this the vector spin of the galaxy, and the vector orientation of the filament. So this is what we call how we parameterize the spin filament alignment. In particular, we use the absolute value of the cosine of this angle. So this means that a value towards 0 means a more perpendicular alignment, while a value towards 1 means a more parallel alignment. And then we study the distribution of the alignments as a function of different galaxy properties. In particular, we focus on stellar mass, bulge to total flux ratio, bulge mass, then the degree of ordered stellar motion, age, kinematic misalignment between gas and stars within the galaxy, and also environment proxies such as the distance of the galaxy to the filament spine and the local galaxy density. And of all these bunch of properties, we found that the mass of the bulge is the property that shows the strongest correlation with spin filament alignments. In fact, if we look at the partial correlation coefficients, so we take into account the correlation of the alignments with the mass of the bulge, there is nothing left for the other galaxy properties. So they just show correlations because they actually correlate with the mass of the bulge. Then we also apply partial least square regression technique, again, to find how many parameters and which parameter can explain most of the variance in the spin filament alignments. And we found that around 70%, so most of the variance is explained by only one parameter, which is the mass of the bulge. So we found that the bulge mass is the primary parameter of correlation. And in this plot, on the left, I have the probability distribution function, and on the x, the spin filament alignment angle from 0 to 1. And we divided galaxies according to the mass of the bulge. And we can see that galaxies that have low bulge mass tend to have more parallel alignment. So this one in blue, you can see that they tend to have a value towards 1, so more parallel alignment, while galaxies that are more massive, so with the mass of the bulge, so for higher values of the mass of the bulge, they tend to have a more perpendicular alignment, so values towards 0. So we have a flip of the alignment from parallel to perpendicular, so this flip is according to the mass of the bulge. So these are the most significant tendencies that we can find when we also divide galaxies according to the other galaxy parameters. So we found a link between the growth of the bulge and the flipping of the spin filament alignments. And if you look at the physical processes that can cause this, these are mergers. So the observed link can be explained by mergers, which are responsible for both these features in the galaxy. Then if, again, we look at different galaxy properties, such as visual morphology, star formation activity, degree of rotation, or environment, and we divide galaxies for those ones that have low bulge mass on the left, and those ones that have high bulge mass, we can find that they show a more parallel or more perpendicular alignment, again, with respect to the mass of the bulge. So the other parameters are just secondary tracers of the alignments with respect to the mass of the bulge. And finally, if we look at the separate spin filament alignments for bulge and disks, so on the left is for bulges, on the right is for disks. Again, this is the probability distribution function for the cos gamma angle, and galaxies are divided according to the mass of the bulge. On the left, we can see that bulges tend to have a more perpendicular alignment, no matter the mass of the bulge. So this means that mergers is the main channel of formation for these galaxy components. Instead, if we look at the disks, we can see that we found different spin filament alignments according to the associated mass of the bulge. And so this means that there can be multiple channel of formations that lead to the formation of disks. So more perpendicular alignment. So more perpendicular alignment will mean that the disk is showing sign of mergers, while a more parallel alignment will mean that the disk has been formed mainly by gas accretion. So to conclude, we found that the bulge mass is the primary parameter of correlation with spin filament alignments, and the observed link between the assembling of the bulge and the spin filament alignments trend can be explained by mergers. And then if we look more into the galaxy components, such as bulge and disks, this can reveal additional clues about the particular formation pathway that galaxy has followed. Now, there's still a lot of unresolved questions. So again, that we are interested in is to understand what's the role of the black hole activity in these alignments, in particular instantaneous activities such as AGNs, but also the integrated activity of the black hole. And then what is the role of the local environment? And we are particularly interested in the outskirts of in the filaments that populate the outskirts of clusters, because that's where pre-processing is happening. And in particular, to answer these second questions, we're going to need the upcoming Hector Galaxy Survey.